Hey everyone, welcome to the channel. Today we are diving into a fundamental concept in fluid mechanics, the hydrostatic equation. Whether you are a physics student, an aspiring engineer, or just someone curious about the science behind everyday phenomena, this video is for you. So let's get started. Have you ever wondered why your ears hurt when you go deep inside the swimming pool or when the aircraft suddenly changes its altitude? This change in pressure with depth or altitude is what hydrostatic equation helps us understand. Static equation is only applicable on a static fluid. So for example, if you want to find out the pressure at the depth h of a swimming pool, let's consider a stationary fluid element at that depth. I'll enlarge this cubical element. Let the height be dh and the surface area of each side of this cubical element be A. Let the pressure acting on the lower surface of this cube be P, and the pressure acting on the upper surface be P plus dP. So dP here is the change in pressure as we move from the lower surface of the cube to the upper surface. All the pressure which is acting sideways on the cube will cancel out each other since they will be equal in magnitude. So we will not have to take into account these pressures. Apart from this, there will be a gravitational force mg which will be acting downward on this cubical element. Now we know that this cubical element is static and it's not moving. So all the forces on this cubical element will be in equilibrium. As we discussed earlier, all the forces which are acting sideways on this cubical element will be equal in magnitude and they will cancel out each other. So there will be no net force along the x-axis. However, we know that this fluid element is completely static. So the net force along the y-axis must be 0 too. The net force acting along the y-axis of this cube will be equals to 0. Now we break down all the forces acting on this cube in the equation. We have the force acting on the lower surface of this cube, let's call it Fl. The force acting on the upper surface of this cube, let's call it Fu, plus the force which is the gravitational force acting on this cube. The sum of all these forces will be equals to 0. Let's solve the equation further. Now, according to the standard convention, let's take the force which is acting upwards on this fluid element as positive, and let's take the force which is acting downward on the fluid element as negative. So Fl is the force acting on the lower surface of the cubical element which is acting upwards. So this will be equals to P times A. Fu is the force acting on the upper surface of the cubical element, but it is acting downwards. So it will be minus P plus dP times A. The gravitational equation will be acting downwards and will be equals to mass times gravitational acceleration. Mass of the fluid element will be equals to the density of the fluid element times its volume times the gravitational acceleration. We will equate this to 0. Solving the equation further, we get P times A minus P times A minus dP times A minus rho times. Now the volume of this cubical element will be surface area of this cube of one side times the height multiplied by gravitational equation, and the sum of all these will be equals to 0. Solving further, we cut out p times a, then we have dp times a is equals to minus rho times a times dh times d. We cut out a from both the sides, and then we have dp is equals to minus rho g dh. This is the hydrostatic equation. Now notice that the value of dp is coming out to be negative. This means that the pressure which is acting on the upward surface of the cube, which is p plus dp, will be lower than the pressure acting on the bottom surface of the cube, which is p. Hence, it is proved that the pressure inside a static fluid increases with depth and vice versa. This is also the reason why you feel pressure in your ears while you dive deep inside a swimming pool.